Hello. In this video, we are going to look at two new convergence tests for series, the comparison test and limit comparison test. Now, these are two really great tests because they're pretty versatile. It takes a big chunk of types of series and allows us to figure out whether they converge or not by comparing them to a simpler series that we already know the convergence or divergence of. So let's start with comparison test. Now this one, the tricky thing is getting the inequalities right. So it's nice to just kind of have these in front of you when you're working on these problems to make sure you get the combination right. So the idea is you're given a series, you're going to come up with a simpler version of the series you're given. So usually just focusing on like the leading terms and any like constant terms or things, you just kind of drop those off and hopefully you get a simplified series that ends up being like a geometric series or a P series or something like that. And so what you need to do though is whatever series you come up with, we'll call that Bn, that's your comparison series. If that is a convergent series, and if it's always bigger than the given series, then we can say that the given series is convergent. Okay, but the Bn has to always be bigger, so it's very important that you state that fact when using this comparison test. Now, if Bn is divergent, then it has to always be smaller than An, the given series. And then that would mean that the given series is also divergent. Okay, so the two things you need to figure out when you're using this test is you need to figure out whether your Bn is convergent or divergent and which series is bigger. If you end up in a situation where you have a convergent Bn that is always smaller than the given series, so it doesn't fit either one of these combinations here, then it probably means instead of using comparison test, you want to use the limit comparison test, which is the second one we're going to look at today. So keep that in mind. If this one doesn't work, I usually try this one first because it's faster. And if it doesn't work, then I take that same Bn comparison series I came up with and do limit comparison test instead. Now, something else to keep in mind is that only non-negative terms can be in the series. So if you have a term with a negative in there, you cannot use the comparison test or the limit comparison test. You have to go to something else on the list. Okay, so keep that in mind. It's an important detail. Okay, so let's do an example. I have the series 1 over 2n squared plus 1, and I need to prove whether it converges or not using the comparison test I'm being told. Okay, so first thing I'm going to do is come up with a similar series to this one. And really, if I just drop off the plus 1 on here, then I end up with a pretty simple series that hopefully I can use for the comparison test. So that's what I'm going to use. I'm going to let Bn just be a simplified version of this where we drop off the plus 1. And then if I compare those two, well, it's going to turn out that my Bn is always bigger. And I can figure that out because the numerators are the same for these two series. And if I compare the denominators, I have a bigger denominator, which means a smaller fraction. And so if you have trouble with that, just, take two actual series like 1/4 and 1/2. 1/4 is smaller than 1/2, and it has a bigger denominator. So bigger denominator means smaller fraction. Smaller denominator means bigger fraction. Okay. So this is going to be true for all n values, and I can do that just by the explanation I just gave. I can figure that out. And so the next step would be to actually figure out whether 1 over 2n squared is a convergent or divergent series. And it turns out that this is a P series where P is 2, and that makes it a convergent series. So now I have the right combination of a series that's always bigger and converges. And so I can use the comparison test because I have that right combination. And so I can conclude that An is also convergent by the comparison test. So I've hit all the pieces that I need to prove this. And it didn't take too much work, but it's really important that you include all this. You need to identify your comparison series, identify whether it's bigger or not, bigger or less, greater than or less than An, prove the convergence or divergence of Bn, and then your final statement about An and the test used. Okay, so there's a lot of little elements there you want to make sure so that you have a complete explanation. But it does go pretty quickly once you get the hang of it. Okay, so let's say though that I had this same combination, but maybe BN was always smaller, then this test wouldn't work. But I can still use that BN and use it on the limit comparison test. And the limit comparison test, again, requires positive terms. Okay, so just like comparison test, if there's negatives in there, can't use it. And this time, you come up with your BN, and then you take the ratio of the two series, the nth terms, so AN over BN, where BN is your comparison test. And if you get a limit where L is a positive real number, so something greater than 0, then either both series converge or both diverge. Okay, so it's kind of similar to the comparison test. We just have this limit in here now. And so really what we're looking for here is we're looking for a simpler version of the series we had, just like with comparison test. And the idea is that they have the same end behavior, because that's what this infinite limit really is looking at, is end behavior. So if they have similar end behavior, then if one converges, the other one converges. If one diverges, the other one diverges. Okay, so let's give this one a try. So kind of a nasty looking series. I've got this root with a polynomial in there. And so again, I want to take a simplified version of this to compare to it. And so here I would just drop off the -1 for sure. And even the 10n, I'm just going to drop. I'm just going to focus on the leading terms and keep the constant on top. If it had been something other than 1, I'd keep it as whatever that number is as well. Okay, so these two series are going to have the same end behavior. They're going to act the same because all I really did was drop off a few extra terms. And if we're going to infinity, they're still going to behave the same. And so this new BN, I can simplify it, and I can even write it as 1 over n to the 3 halves. Okay? And then all I have to do is set up that limit. So I take the original series over the comparison series, and I'm going to simplify this a little bit. So I'm dividing fractions. So that's the same thing as multiplying by the reciprocal of that bottom fraction. And so I get n to the 3 halves on top. And actually, I just turned that half into a root so they can both be in the root. So there's a lot of simplification going on there. You might want to pause it and just take a look at that for a second before continuing. Okay, so now I can go forward with this limit. And so really the leading terms is what we can focus on here. So this is going to be equal to the limit of just the leading terms inside of the root, which just simplifies to 1. So I get 1 for the limit. And again, for this test, you need to get a limit that's positive, so something greater than 0, which I did here, which means the test worked. Okay, so where we're at, we came up with our comparison series. We did the infinite limit of the ratio of them. The next step is I need to actually prove whether BN converges or diverges. And whatever it does, my original series will do as well. So it turns out, well, that is a P series where P is 3 halves, and that's greater than 1, which means that the series converges. Okay, so I've included all of the explanation of how that converges and why. And well, because that converged and our limit was something positive, I can say that the original series AN also converges by the limit comparison test. And that's how this test works. Okay, make sure you get all of those elements in there. Really, everything that you see on the screen is necessary for a full explanation here. So keep that in mind as you practice. And here's a couple of more examples for you to try out. It's a good idea to try out both tests and see if it doesn't work. You don't want to get caught trying to use the comparison test and then not get the inequality right and not notice that it doesn't work. Okay, so keep that in mind as you give these a try.